it's working. Yeah. All right. So what we're going to do today is we're going to go through the 2014 Exam 2 from spring for Physics 208, and this is the University Physics 208, not the Don't Panic one. So let's take a look at this first problem, and let's see how to go about doing it. So what this says is that in the two circuits given below, all light bulbs are identical. The batteries are also included. Which of the following correctly indicates the relative brightness of the bulbs? Okay, so what we want to do is see which bulbs are going to be brightest. So between A, B, C, and D. Now, one thing you need to know about the brightness of bulbs is that it's going to be directly proportional to your power. And so there are three equations for power. Power is equal to I times V. Okay, it's also equal to I squared times R, and it's also equal to V squared over R. And so what I need to do is basically looking at these circuits, I'm going to try to see which of these would have the similar example. Let's take a look. It's a lot easier with a picture. So I wish I can kind of have the picture for y'all, but you have this one right here. And so this is going to be bulb D. And then here we've got bulb B and C. And then in this one we've got bulb A. Bulb A. Okay. So looking at these three equations for power, the I times V, the I squared times R, and the V squared over R. I want to see between these three equations, I'm more looking at the I and I'm looking at the V. And whenever you have resistors that are in parallel, the voltage is constant. Whenever it's in parallel, the current isn't. The current splits. So this I squared times R and this I times V, these are not good equations in order to see which would be brightest because the currents aren't constant. But you know what? Your voltage is. Now, if power is equal to V squared over R, take a look at this B and C. The same voltage that goes through here is the same voltage that goes through here, which is the same voltage that goes through here. So all we need to do is we got to check the relationship between the resistors. Now here, B and C, okay, these resistors are going to be in series. If I want to find RBC, RBC is simply going to be RB plus RC. The point is this is going to be a higher resistance than A and D. Since all these bulbs are identical, the resistance through A and the resistance through D is equal. The voltage through A, the voltage through D is equal. So I already know the power of A is equal to the power of B. And we know that the power through B and C, since this is bigger and these are the same, I know the power of B is equal to the power of C. However, since this resistance, overall resistance, is bigger, overall that would make the power smaller, the power of D. Okay? And so that's why the power through A is equal to through the power of D, which is going to be more than the power through B and C, even though they're the same. So now let's go ahead and take a look at the second one. So taking a look at this second one, it says in the circuit given below, both capacitors are initially uncharged, okay? And let's bring that kind of closer in, so you kind of, not that one. I'm going to take this guy over here. Okay. And so it says in the circuit below, the capacitors are initially uncharged. That uncharged is extremely important, okay? Uncharged with VB equal to 15, R1 is 3 ohms, R2 is 5 ohms, R3 is 7. You've got all the different capacitors. How much current will flow through R1 just after the switch is closed? Since they are initially uncharged, we need to be aware of which direction the current is flowing. So let me kind of sketch out the circuit for y'all. Then I'm going to move this guy out of the way. Okay, let's see. be our circuit. Okay. I think that'll be good. So we have a resistor, and then we've got a resistor coming around like this, with a capacitor, and coming around, we got another resistor. That switch will end up being closed, and we have another capacitor. Here's my R1, and then we'll go R2, R3. 2, 3, and we got C1 and C2. Since these capacitors are initially uncharged, okay, since they're uncharged, I know that the direction the current is going to flow, it's going to flow around R2, okay? It is going to flow around R2. It will not go through here. And so, since there's no junction, R1 and R3 are said to be in series, and so there's some voltage V. And so, since they're in series, my Req is going to be R1 plus R3, which, let's go ahead and see what R1 and R3 were. Let's see, R1 was given to be 3 ohms, 3 ohms, R3 was 7 ohms, and so the Req is 10 ohms. And also remember that resistors in series, they share the same current. Current is conserved for resistors in series. And so, we're going to use that our V total is equal to total times Req. And so, I can find my total currents by doing the V over R, which the voltage on this battery is given to be 15 volts. We just found the Req is 10 ohms, and so the total current flowing through this is 1.5 amps. And because R1 and R3 are in series, then the current that goes through R1 is equal to the current that goes through R3, which is equal to the total current overall, which is why the current that flows through R1 is 1.5 amps. That's it. So, now that we've gone through that one, let's take a look at number 3. So number 3. Okay. Let's read this guy. So what it says 120 volt main electric outlet. Here we go. Main electric outlet has a 15 amp circuit breaker. A 1000 watt refrigerator is plugged into this outlet. You want to plug a few more devices on to the same main outlet. You have 3 devices with power ratings of 700, 850, and 950. Which of these can you plug in without blowing the fuse? Okay. So I'm just going to pull this up to the side. And so I've got my 7. Scroll it over a little bit. So we have the 7, the 850. Well, I can't really see too much, but your extra devices are going to be the 700, the 850, and the 950. Now you're going to blow a fuse, okay? You're going to blow a fuse whenever the power that is being connected is greater than whatever you have. And so in this case, we got to figure out what the power of our main electric outlet is. Now notice how they give me a voltage. They give me a voltage of 120 volts. And they give me a current of 15 amps. So if I want to find the total power that can be held by this outlet, I'm going to use the I times V, which is going to be 15 amps times 120 volts, which is going to come out to 1800 watts. And so any power greater than 1800 watts is going to blow your fuse. So your fuse will blow if you have too much power connected to it. And so we already have a 1000 watt refrigerator, right? We already have a 1000 watt fridge. And so anything more than 800, and this is going to blow. And so that's why you can only connect the 700. If you connect the 850, or if you connect the 950, what's going to end up happening, you're going to blow your fuse. And so that's why in this example, it's going to be only the 700. And so that's going to be A. Finally, I believe we have one more. We've got one more multiple choice before we move on to the workout problems. Okay. So let's take a look at this guy. So what it says is that it says a capacitor, okay, with no dielectric between the plates, is connected in series with a resistor and a battery and allowed to acquire a maximum possible charge for this setup. With the capacitor fully charged, the battery is still connected to the circuit, a dielectric is inserted between the plates of the capacitor, assumed instantaneously, and the circuit remains connected in this setup for a very long time thereafter, so assume infinite time. If QC is the charge on the capacitor and VC is a potential drop across its plates, then which of the following statements is true about QC and VC after the dielectric is inserted as compared to the case without the dielectric? Okay. So what is a dielectric? What exactly does it do? Well, we know that the charge that a capacitor can hold is equal to C times V. And what I'm going to say is that when you insert a dielectric, we'll call it CF. CF will be the capacitance after you insert the dielectric. This is going to equal K times C naught. And this K is your dielectric constant. And so, now that I know that my capacitance goes up, by definition, if your capacitance goes up, your QF, we'll call it QF, your final charge, is going to be K times your initial capacitance times V. In essence, your Q increases. But just because you put a dielectric in front doesn't mean that the voltage changes. It says that it's going to be connected there for a very long time, assume infinite time. Your voltage will have no change. That's it. So that would be answer choice C. Your QC increases, but your VC is going to remain the same. Okay, so now that we've gone through the multiple choice questions, let's go ahead and see if we can attack. Oh, whoops, I did not recognize. How about that? Okay, so that's what's going on. Basically, your CF is equal to K times C naught. Capacitance goes up. Capacitance goes up. The amount of charge that can be held goes up. But after an infinite long period of time, your voltage is not going to really have any change. All that's going to change is the amount of charge that those capacitors can hold. So now that we've done that, now let's go ahead and go to a workout problem. So first workout problem. Nope. Okay. Let's take a look at this. What it says is, see if we can see it all. All right, cool. Okay, so we have a DC circuit that has a source of EMF and 4 different capacitors as shown in the figure below. Assume the capacitors are fully charged and that there is no current in this circuit. The EMF of the battery is 200 volts and all the capacitances are given. What we want to do is find the charge on each capacitor. Okay, so what we need to do is remember the rules to the game that I talked about. And once we remember those rules, then we just apply them. And what those rules were is that if you have capacitors in parallel, so I have capacitors in parallel, the way that we're going to find the equivalent resistance is my CEQ is going to be C1 plus C2. Now here the voltage across, so this is going to be C1 and C2. The voltage across each are the same, so V1 equals V2, which equals V total. And then finally though, the charge isn't. Q1 most definitely does not equal Q2, okay? In fact, Q1 plus Q2 is equal to the total charge that'll flow through that system. So that's going to be the rules for parallel. And the rules for series, for capacitors in series, are as follows. In order to find the equivalent capacitance, the 1 over CEQ is equal to 1 over C1 plus 1 over C2. And voltage is not conserved over capacitors that are in series. And so the V1 most definitely does not equal V2. It can if the capacitances are the same, but if they're not, they don't. And so what's going to happen is that the sum of V1 plus V2 is equal to V total. And then finally, though, across in series, your charge will in fact be the same. Q1 will equal Q2. Okay, so now that we have these rules, let's take a look at this circuit, and then let's see what happens. Sorry. And so this circuit, basically, so I'm going to go out over here. This, we got point A. B. And then we've got our EMF down here. And we're going to go C1, C2, C3, and C4. So what it says is find the charge on each capacitor. So we've practiced using these rules before. We know how to deal with these so long as we follow through them. So what we first need to do is we need to find our equivalent capacitance. So regardless of your type of situation, the first thing you will always do, whether it's a circuit with capacitors or a circuit with resistors, is find your equivalent capacitance. Because we know that Q total is equal to CEQ times V total, which means that I already have my total voltage. That was the 200 volts. I need to find equivalent capacitance so I can find my total charge. And once you have total voltage, and once you have total charge, then you actually have the ability to then answer whatever it is that they ask. So let's find CEQ. By the way, let's see, these capacitances are given. So 10, 20, 30, and 50. 10, 20, 30, and 50, and all of them are all microfarads. Okay, so let's go ahead and find CEQ. First thing is I'm going to find C12. And so I know that 1 over C12 is equal to 1 over C1 plus 1 over C2. They are in series, and so since they're in series, it's going to be 1 over 10 plus 1 over 20, which means that 1 over C12 is going to be, well, it'll be 2 plus 3, so it'll be 3 over 20, which means that C12 is 20 over 3. So now that I have C12, it's going to be this guy right here, let's go ahead and find C34. That way I can basically treat these now as just two capacitors. So I'm going to find C34. So 1 over C34 is equal to 1 over C3 plus 1 over C4, which is going to be 1 over 30 plus 1 over 50. This is where a calculator definitely comes into play. That's 1 over 30 plus 1 over 50. And so it's going to come out to 4 over 75. 4 over 75. And so what that tells me is that 1 over C34 is equal to 4 over 75, which tells me that C34 is 75 over 4. And now that I have C12, so C12 is basically like one big capacitor up here, and I've got C34, a big capacitor there. Now these capacitors are in parallel, and if they're in parallel, then it's simply the straight up sum. And so I know that CEQ is going to be the 20 over 3 plus the 75 over 4, which, let's go ahead and throw all that in in our calculator. So 20 over 3 plus 75 over 4 is going to be, let's round to 25.4. Use decimals, round to that. So 25.4 microfarads. And now that I know that CEQ is 25.4 microfarads, and now since they gave me the total voltage of the entire system, I can finally find Q total. And it's always going to be your setup. Whenever you start, always start off by finding your equivalent capacitance or resistance. That way you can find your total either charge or current. But anyways, in this case, Q total is going to be 25.4 microfarads times, I believe the voltage was 200 volts, right? Voltage, right, was 200 volts. So whenever we throw this in our calculator, let's swap out 200. Q total, let's go 5083. So we'll round to 5083 microcoulombs. So what I'm going to do is off to the side, I'm going to write all that really important piece of information. We know V total is equal to 200 volts. We know that CEQ is equal to 25.4 microfarads. And then finally, your total charge over everything is equal to 5083 microcoulombs. Cool. Now that we have that, we need to utilize these rules about the conservation of voltage or the conservation of charge, depending on whether it's in series or in parallel, to find the charge on each one. So, I'm going to give myself a little bit of space, but hopefully I'll have this down in order to how we found CEQ. Because now what we need to do is find the charge on each capacitor. Alright, so we know what the total voltage is, and whenever I have things in parallel, voltages are the same. And so I know the voltage that'll flow through and the voltage that'll flow through there are going to be the exact same. I know the voltage through the system 1-2 is going to be the voltage through the system 3-4, which is going to be 200 volts. We do know that. However, your charge is, well, it's not going to be the same, but it's going to be the sum of that. So what we can do is, if I want to find Q12, the charge that flows through both of those, I know that Q12 is going to be C12 times V12. And we saw earlier that C12, we calculated this just a second ago, that was your 20/3 microfarads. And so, the charge is going to flow through here is going to be the 20/3 microfarads times V12, the voltage that flows through there, will be the total voltage of 200 volts. When you throw that into the calculator, 20/3 times 200, what you get is, we'll round to 1333, this will be microcoulombs. And guess what? Because the charge is constant, is the same through series, the charge that goes through both 1 and 2 are exactly the same. So I've already found Q1, 1333 microcoulombs, and so is Q2. Q2 is also 1333 microcoulombs. And if that's Q1 and Q2, whenever you have things in parallel, the total charge is going to be equal to the sum of the charge that goes through the top one plus the charge that goes through the bottom one. And so what that means is that Q12, the charge that goes through both of those, Q12, plus the charge that goes through 3 and 4, Q34, is equal to your total charge. And guess what? Our total charge is 5,083 microcoulombs. And so what this tells me, the Q12, this is 1333, plus Q34 is equal to your total charge of 5083. All these are, of course, in microcoulombs. And so Q34, let's subtract that over, 5083 minus 1333, that's going to be 3750. 3750 microcoulombs. And because C3 and because C4 are in series, the charge that goes through this entire, I guess, wire, we can say, is the charge that goes through both capacitors. Which is why Q3 is going to be the 3750 microcoulombs. And the Q4 will also be 3750 microcoulombs. And that answers part A. Part A said, what is the charge that goes through each capacitor? And now in part B, let's see, what does part B say? Part B states, find the potential difference. Let's go ahead and bring this over. Find the potential difference, VAB, between the points A and the points B. So all we're going to do is, what's the difference in voltage between here and between there? Okay, it's not going to be too bad. Because what's going to happen is we're going to take this voltage that goes through here, and let's see how much is left after C3. And I'm going to take this voltage, so this is going to be, we'll call it 1, we'll call it 2. I'm going to see what's the voltage difference when I go from the battery to B, what's the voltage difference when I go from the battery to A, and then once I know the total voltage difference, then I'm just going to subtract those two values. Let's go ahead and put it into practice, that way you can see what I mean by that. So, what's going to happen, you have a couple of options. I think that's the option I'm going to go. Your V of A, voltage at A, is equal to your EMF minus, if Q is equal to C times V, V is going to be Q over C. So this is going to be Q1 over C1. And your V at B is going to be your total voltage minus, we lose some of that voltage through that capacitor, and so it's going to be Q3 over C3. And fortunately for us, we've already got all those values. And so V of A is going to be your EMF of 200 volts minus my Q1, which is the 1333 microcoulombs, over C1. C1 is 10 microcoulomb. Oh, just kidding. Microfarads. And so when you do 200 minus all that, so 200 minus 13.3, we would have 66.7, 6.7 volts. Now if you want to find the V through B, this is going to be your 200 volts minus Q3. Q3, that's your 3750 microcoulombs, divided by C3. C3 was 30 microfarads. Let's go ahead and throw all that in the calculator. It's be 200 minus the 3750 over 30. And so it's going to be 75. It'll be 75 volts. And so if I want to find the potential difference, I guess it just says exactly what's the potential difference between points A and B. It doesn't matter if you do VB minus VA or VA minus VB. You're just looking for the difference. And so VB minus VA, this is just going to be, to go from here to here, it's going to be 8.9. And so that's what I was talking about with the rules of the game last time. Know the rules of the game, know how to find your equivalent capacitance, and then from there, you all should be good to go. So that was a pretty tough one. I mean, that one basically incorporated your knowledge on, well, just about everything. So, with that being said, let's flip it over, and let's now get to our next problem. Okay. Let's take a look at this one. Let's get this over real quick. There we go. Okay. So what this says is that a DC circuit that consists of two sources of EMF with internal resistance little r and a load resistance capital R is shown in the figure. EMF of the sources, their internal resistance, and the resistance of the load is known. We know both batteries, we know all the resistors. Part A, find the magnitude and direction through the load resistor, find the power dissipated through the load resistor, and then once again, find the potential difference between points A and B. Okay, so, I'm going to scoot this off to the side. I wish the circuit was on the other side, but we'll be okay. So let's go ahead and redraw. Let me draw that circuit. What we're going to be doing in this problem, definitely going to be wanting to use Kirchhoff's rules. So, draw on this circuit. We have a resistor right here. Battery. And this is going to be pointing to B. This is going to be a little r. And then we're going to have another battery here. This is EMF 1. This is EMF 2. Another resistor, another little r. And then here's our big load resistor, capital R. Now, little r, for both of these are all 5 ohms. For the big resistor, we have 15 ohms. And then for EMF 1, it's going to be 15 volts. And then EMF 2 is going to be 50 volts. Okay. And what we want to do is, in part A, I want to find the current that goes through that resistor. Okay. Alright, so we take a look at part A. Part A, find the magnitude and direction of the current that flows through that load resistor. Okay. So let's go ahead and definitely utilize Kirchhoff's rules. Something like this. So just pick a junction. Doesn't matter which one. Go ahead and pick this junction right here. And the reason I want to do that is I want my current to flow going from positive to negative. Right? You always go from positive to negative. So let's make this I1, and this will split here into I2, and this will split here into I3. And so using his first rule, using the junction rule, we know that I1 is equal to I2 plus I3. And in part A, if I want to find the current that flows through this big R, my entire goal for part A is to find I3. I3 is going to flow through R. Now notice how both actually all three, the I1, the I2, and the I3, are all unknown. Since they're all unknown, those are 3 unknowns. 3 unknowns means 3 equations. 3 equations means I need 2 more loops, since I've already got 1 equation right here. And so for my first loop, I think what I'm going to do is I'm going to start here at E2, and I'm going to loop around. So this is going to be loop 1. Okay, so loop 1. I'm going to start off with my voltage E2, which is going to be 50. Then I'm going to lose voltage through this little resistor. So this is going to be minus I1 times that R of 5 ohms. Then I'm going to gain voltage through this battery. It's going to be plus 15. Then I'm going to lose voltage through this resistor. So it'll be minus I2 times 5. And we know the sum of any enclosed loop is going to be 0. So now that I've taken that as my first loop, for my second loop, I kind of don't want to go in the wrong direction of my current. So I think what I'm going to do is I'm going to start here at E2, and I'm just going to go around the outside. That way I don't have to deal with any weird negative currents or things like that. Everything's flowing in the same direction as the way it should. And so this is going to be loop 2. Okay, so loop 2. I'm going to start off with my EMF 2, which is 50 volts. I'm going to lose voltage through this little R. So minus I1 times 5. Then, let's see, coming around, I'm going to lose voltage through this capital R. So it'll be minus I3 times 15. And that encloses the loop. That's equal to 0. And now what's going on is you got 3 equations, 3 unknowns. Now what you need to do is do a system of equations in order to solve for I1, I2, and I3. But really specifically, we just got to find I3. So here's what I think I'm going to do. What I'm going to do is since I1 is equal to I2 plus I3, I'm going to go ahead and take this I1 and put it into each I1. That way I can take these 2 equations, because we all know how to use 2 equations with 2 unknowns. And so that's exactly what I'm going to do. I'm going to replace I1 with I2 plus I3. That way both of these equations just have an I2 and an I3, and we can solve from there. So, redoing loop 1, I'm going to have, so this is loop 1 once again, we're going to go 50 minus, do I2 plus I3 times 5 plus 15 minus I2 times 5 is equal to 0. I'm going to go ahead and distribute this negative 5 into here, and let's go ahead and add the 50 and the 15. So 50 plus 15 is 65. Then I'm going to have minus 5I2 minus 5I3. This right here is going to be a minus 5I2 is equal to 0. Now all of my variables, I'm going to move over to one side and keep that 65 there. So the minus 5I2 and the minus 5I2, when I add that to the other side, I'm going to have 10I2. Moving the I3 to the other side, we're going to have plus 5I3 is equal to 65. So here's loop 1. Let's now do loop 2. So coming over here, let's do the quick math to do loop 2. Loop 2, this is going to be 50 minus my I1 I'm changing to I2 plus I3 times 5. Then I've got minus I3 times 15 is equal to 0. I'll distribute that negative 5 into there. So 50 minus 5I2 minus 5I3 minus 15I3 is equal to 0. And so now moving everything over to one side, moving this minus 5I3 minus 15I3 to the other side, what I'm going to end up having is the 20I3 and 5I2. 5I2, this right here is going to be plus 20I3, and this is going to equal that 50. And now at this point you have a couple of options, right? We have two equations. Here are my two equations and my two unknowns. I would probably choose the elimination method. What I'm going to do is I'm going to multiply this bottom row by a negative 2. That way I can take this 10I2. I can make this times negative 2. That'll be a minus 10I2. That'll cancel out. And then I can isolate and solve for I3, which is really all I care about. All I care about is finding that I3. Multiply this by a negative 2. And so now let's go ahead and rewrite my equations again. I know the math can get kind of messy, but you're just going to have to deal with it, I guess. So 10I2. Hopefully on the exam, the math might be a little bit nicer, but I mean, knowing, y'all as professors, this literally was an exam question. So that's that one. Multiply this by a negative 2 minus 10I2 minus 40I3 is equal to minus 100. Because now I can add these together, and these will cancel out, and I'll have a minus 35I3 is equal to a minus 35, which finally gives me that I3 is 1 amp. And that is how much current goes through that capital R, because, well, that's the current that goes through R. And because it was positive, we know we pointed it in the right direction, and so as for the direction, it's going from left to right. That came out to a positive current. Okay, so that was part A. Finally, let's take a look at part B. What does part B say? Part B says, find the power dissipated through the load resistor. So I want to find the power through there. Once again, I gave you 3 different equations for power. I know the current that goes through there. I know the resistance. And so, because of that power, I'm going to go ahead and use the equation I squared times R, more specifically I3 squared times R, because I3 is the current that flows through there. And so this is going to be 1 amp squared times my R of 15 ohms, which is going to come out to 15 watts. So it's going to be that. And then finally part C. Part C says find the potential difference between points A and B. So here's point A, here's point B, and I just want to see what's the potential difference. What's the difference in potential between A and B? All that's going on is this resistor right here is sucking up some voltage. And so all I want to do is I want to see how much voltage this resistor sucked up. And so for part C, you guys see that? We're still good. Part C, the voltage is just going to be I3 times R. We already know that's the current, so voltage lost through that resistor. we know that's going to be 1 amp times 15 ohms, and so that comes out to 15 volts. That's what I was talking about, okay? With the Kirchhoff's rules, with all these equations that I gave y'all, as long as you know the rules to the game, that's all this is. This is just a really big puzzle, okay? So if you know how to deal with a really big puzzle, y'all will be good. Okay, let's take a look at the next one. I believe we have 2 more workout problems on this exam. Let's go ahead and pull this guy now forward. Alright, so let's take a look at this one. What it says is that a parallel plate vacuum capacitor has 13 joules of energy stored in it. The separation between the plates is 3.6 millimeters. If the separation is increased to 4.5 millimeters, what is the energy stored in part A if the capacitor is disconnected from the potential source before moving the plates? Part B, what if it remains connected and after the plates are moved? Okay, so we have a couple different scenarios. We need to know our equations. Let's go ahead and remind ourselves of the equations for energy between parallel plate capacitors, as well as reminding ourselves what the heck the capacitance between parallel plate capacitors are. Okay, so let me go ahead and move this guy off to the side. All right. So, first off, as for the equations for energy, you have 2 equations for energy. This is going to be Q squared over 2C, and because Q is equal to E times V, we can also say this is CV squared over 2. Throw all that into there. Now for parallel plate capacitors, this is going to be our first set of our equations. For parallel plate capacitors, this is going to be epsilon naught times your A over D. That's A over D. And this would be the capacitance between parallel plate capacitors. Now reading through this problem, it says that our initial amount of energy, go ahead and write down everything good. Our initial amount of energy, we'll call it U0, is equal to 13 joules. And the separation between the plates, it was at 3.6 millimeters. So D0 was 3.6 millimeters, or 0.0036 meters. Then it got moved to 4.5 millimeters. So we'll call DF, our final distance, is going to be 0.00 and then 45 meters. Okay, cool. In part A, the capacitor is disconnected and the potential from the potential source. So basically, your voltage got turned off. In part A, voltage got turned off, and so your charge Q1 equals Q2, which is going to be constant. Okay, your Q is what's charged at constant. So because our charge is what's going to be constant, to calculate energy for part A, I'm going to go ahead and use that second equation. And so what I want to do is I want to find UF. UF is what I'm looking for. And UF is going to be that Q over 2 times CF. Okay, that times that CF. And so, well, you know, CF, according to this, is epsilon naught A over DF. Now we have a small issue. And our issue is we have no way of finding this area. If I could find that area, man, just plug it into here, and you're done. We can't do that. So we got to get a little creative. Let's go ahead and take this equation and let's plug it into here. And so what I'm going to say is that UF is equal to, well, whenever you divide by a fraction, it's as if you multiply by that fraction flipped. And so it's going to be Q dF over 2 epsilon naught A. Like I said, Q1, Q2, constant Q, all those charges are going to be the same. It's your voltage that changed. Your charge didn't. Okay, so we got Q, final distance, 2 epsilon naught A. That's cool. I got too many, I don't know what A is. But you know what, according to this, I know what U0 is. By doing the exact same math, except just changing it to your initial energy, This is going to be Q, which the Q at the beginning is the same as the Q at the end. The only thing different is your initial distance. Your initial distance is different. Over 2 epsilon naught A. Epsilon naught's a constant. A is constant. The surface area, that's not changing. And so what I can do, in order to cancel some of these stuff out, let's go ahead and get a little creative. What I can say is, what am I looking for? UF? So let's do UF divided by U naught. Because if I do UF divided by U naught, I take UF, Q dF over 2 epsilon naught A, and whenever you divide by a fraction, you multiply by that fraction flipped. So it's 2 epsilon naught A over Q d naught. And check this out. The 2 epsilon naught A's, they cancel. These Q's cancel. What we can say is that UF over U naught is equal to DF over D naught. And we have all of that. We have D naught, we have DF, and we've got U naught. And so with that being said, multiply it to the other side, UF is going to be DF over D naught times U naught. And I trust you all can just plug numbers into the calculator. But that's how you would deal here if our charge is going to be constant. That's why I went ahead and used this equation. And then just be aware that for capacitance, it's going to be C as epsilon naught A over D. Your A stayed the same. Your D is the only thing that changed. And so from there, we have to get a little creative to cancel out this more specifically this A. There is no way of calculating the surface area with the given information. And so that's why I had to get a little creative here to cancel out those A's. And so, now that we know that, we're going to use a similar strategy for part B. So now that we have this, let's go ahead and do part B. So exact same situation, except for one small difference. And our difference here, take a look at this, is now the capacitors remain connected to the potential source during and after the plates are moved. And so what will happen is your voltage is going to will stay the same. Your V is going to be constant. So in part B, V1, or I guess we'll say V naught, equals the V at the end. That's going to be constant. We'll call it some voltage V. And so it's because of that in part B, since our voltage is going to stay constant, to calculate energy, we're going to use the CV squared over 2. So once again, UF is what I'm looking for. I'm looking for my final energy. And my final energy is going to be CF times V squared over 2. And we know that CF is equal to epsilon naught A over DF. That's going to be the capacitance of 2 parallel plates. And when I plug that into here, once again, replacing your CF with this, I can say that UF is equal to your CF times V squared. So this is going to be epsilon naught A times V squared over 2 DF. So this is your UF. But once again, just like last time, I can't find, there's no way of knowing what A is. So we got to get a little creative once again. We're going to say U naught is equal to C naught times V squared over 2. And C naught is going to be epsilon naught A over D naught. In essence, we're going to use the exact same math this time to put U naught in terms of everything given here. And so replacing this C, epsilon naught A over D, epsilon naught A V squared over 2 D naught. And now look what happens. Now what we can do, let's get creative once again. Okay, let's go ahead and divide these two. That way I can cancel everything except for these two distances. So if I'm trying to solve for my final energy, UF for U naught is equal to the top fraction is going to be epsilon naught A V squared over 2 DF times, whenever you divide by a fraction, multiply by that fraction flipped, 2 D naught over epsilon naught A V squared. These canceled. These 2's cancel. You get that UF over U naught equals D naught over dF. And now we've got U naught, we've got D naught, we've got dF. All you got to do now is multiply it to the other side. And so your final answer for part B is that initial distance, or that final distance, times that initial angle. So we need to get a little creative. This one was pretty tricky. But that's how you would go about problem number 4. Last problem. Okay, so last problem of the day. We've got an RC circuit. We've got a switch. Freaks people out. You know what? That's okay. Because I'm going to show y'all how to deal with it. Alright, see if I can pull this RC circuit out there. Okay, once again, I wish the circuit was on the other side of the picture. But we'll figure that out. This is kind of just a test trial run. See how it goes. So for problem number 5, it says, in the circuit shown in the figure below, both capacitors are initially charged, so that the charge of the positive plate of the capacitors, Q initial, is 0.45 millicoulombs. C1 is 20 microfarads, C2 is 30 microfarads, R1 is 30 ohms, and R2 is 50 ohms. Part A. How long after closing the switch will it take for the charge on the positive plates of the capacitors to be reduced down to 0.1 millicoulombs? And then what's going to be the current at that time? Okay, so notice how we've got a couple resistors in parallel and capacitors that are in series. So let me go ahead and sketch out that picture for y'all, that way we can see it. And then we'll go ahead and talk about the equations that we're going to use. Hopefully you recognize, since this is an RC circuit, your charge will either grow or it'll decay. And the problem says we're starting with 0.45 millicoulombs. We're ending with 0.1 millicoulombs, so hopefully you recognize that you're decaying. Okay, so what do we got? We got this, the switch, this. We got a couple resistors in parallel. And then, well, this is all you got, that's good. And here we got a couple of capacitors. R1, R2, and C1, C2. Okay. So what we want to do here is we recognize that the charge on this is decaying. Because when you flip that switch, that these capacitors will start to decay. And the equation that I gave y'all for that is that your final charge is equal to your initial charge, e to the negative t over rc. And what I emphasized about that r and about that c, that's going to be your r is going to be your equivalent resistance, and your c is your equivalent capacitance. Make sure you're aware of that before you even begin to utilize this equation. If you have multiple resistors and multiple capacitors, then you got to find the equivalent resistance and equivalent capacitance first. So let's find that really quickly so that I can utilize this equation. So REQ, in fact, actually these are in parallel, so because those are in parallel, 1 over REQ is equal to 1 over R1 plus 1 over R2, which, let's see, what was R1 and R2? R1 was given to be 30 and then 50, so it's going to be 1 over 30 plus 1 over 50 ohms. So I get that 1 over REQ. Let's go ahead and throw that into our calculator. And so we have 1 over 30. 30 plus 1 over 50 is going to be, we'll go 0.053, or round. And so flipping that, we get that REQ. We're going to raise that to the negative 1. We get 18.75. So 18.75 ohms. Now we've got to do the same thing for our equivalent capacitance. And once again, notice how our capacitors are in series. Capacitors in series means we have to, well, do the fraction thing again. So that kind of stinks. But 1 over CEQ is equal to 1 over C1 plus 1 over C2, which, let's see, where am I? So 20 and 30. So this is going to be 1 over 20 microfarads plus 1 over 30 microfarads, which, let's go ahead and throw that into our calculator. 20 and 30. 1 over 20 plus 1 over 30 And so it's going to be 0.083. 0.083. And so flipping that, your equivalent capacitance is going to be 12. 12 microfarads. Okay. So in this equation, in our decaying equation to find that final charge, okay, I'm going to use 18.75 into my R, and I'm going to use 12 times 10 to the negative 6 into my C. Now they give me the initial charge. They told me in the problem that your initial charge is 0.45 millicoulombs. And they told me, it says, when will the final charge be 0.1 millicoulombs? And T is what you're looking for. And so now we're just doing kind of basic algebra, kind of some Cal 1 algebra, in order to find out what T is. So first thing I'm going to do is I'm going to take this Q naught, divide it to the other side. Now that we have this, we're going to do E to the negative T over RC is equal to QF over Q naught. At this point, you take the natural log of each side, so that negative T over RC is equal to the natural log of QF over Q naught. And finally, multiply that negative RC to the other side, you get that T is equal to negative RC ln of QF divided by Q naught. Just plug it in. Your R used 18.75. For C, it's a microfarad, so make sure you do 12 times 10 to the 6 farads. Okay, with this one, you have 0.45 millicoulombs. And so for the Q naught, make sure you do 0.45 times 10 to the negative 3 coulombs. Okay, remember, millicoulombs, just do times 10 to the negative 3 to go to coulombs, right, yeah. And so with this one, also same thing, 0.1 times 10 to the negative 3 coulombs. And now that you have QF and Q naught, now that you have the R and the C, you just plug into there. And then for the last part, part B, if you take a look at that, it says, what will the current be? What will the current be at this time? And so if I want to see what's the current, well, what did I say current was? If you really remember the very first time I ever introduced current, I said current, I, go ahead and a little bit of space, I is equal to the rate of change. It's however much charge comes in per second. It's basically the derivative of charge. And so if you take a look at this equation, if Q is equal to Q naught e to the negative T over RC, then dQ dt, if I take the derivative of this with respect to T, it's going to be a negative Q naught over RC e to the negative T over RC. What will happen is you will already have found your T here in part A. The RC, we already have R and C, and we already have Q naught. Now I know this says negative, whether it's a negative current, positive current. Remember what I said, positive and negative tell you nothing more and nothing less than direction. So if it wants the magnitude of the current, just make that number positive. That's it. You know, that is the Spring 2014 test, and that's why everything that I wrote there on that dry erase board was so important in all those lectures, because all I did was kept referring to that the entire time. So hopefully this helped. Let's see if we have any questions. Let's see, it's just me. Okay. So if anybody has any questions, I'll leave this going for another 30 seconds or so. If I don't see any questions. If you have any questions, just let me know. Otherwise, hopefully that helped out a lot. I'll give you all about 1 minute to see if any questions come on. Otherwise, good luck on your test tomorrow, and I will see you guys next week for sure. Okay, so we have a question here. It says, can you explain how to get I from problem 5? Sure. So let's go back to problem 5. Oh, that's the problem. Problem 5, is that the problem that we just did? Because there's, oh, okay, yeah, find current. So if you want to find current, you want to find the I through problem 5, remember current is simply just the rate of change of your charge with respect to t. It is literally the derivative of this function with respect to t. So, just real quickly, if I said that, let's just say that y is equal to e to the 3t, dy dt, the derivative of this, well, you just multiply that number in front, right? 3e to the 3t. And that would be your derivative. And so all that I'm doing here to find my current is going to be the derivative of my charge. And the number in front of that t, think of it as like negative 1 over RC. And so I take that negative 1 over RC, multiply it in front. That's the derivative of that function. And then we've already got RC, Q naught, and the t we would have found earlier from there in part A. So hopefully that answered that question. Any other questions? Like I said, I'm basically going to be on here until y'all are out of questions. And if y'all are good, then man, y'all are good. Thanks. So, looks like we're all out of questions. Like I said, whenever I see y'all again next week, if y'all can give me any feedback as to what you liked, what you didn't like, what can be better. Right now, I'm kind of doing this on a webcam. So, we're going to definitely do this on a camera next time. But this is kind of just the start to what we're going to do. And so, definitely any feedback next week would be much appreciated. All right, let's see. We got a couple of questions. Can you walk through how you set up question 4 again? Yeah, sure. And then would it be possible to do another problem from a different exam? Yeah, if you send me that problem somehow and can send it to me through the chat, I'm not sure. Like I said, we're kind of figuring this out as we go. Let's see, number 4. Yes, okay. So I'll kind of walk through the basics of how I set up number 4, and then you can always rewind to see the math behind it. But what I was doing with number 4, sorry, I have my dog, the German Shepherd, name's Maddie, kind of chilling out here. So if you see me stepping over something, that's stepping over her. Okay. So there are 2 equations for energy. So for number 4, energy was it was Q squared over 2C, and it's also CV squared over 2. And so what I did, okay, and if you want to see the math, you can rewind. But if you want to see what I did for part A, it says if the capacitor is disconnected from the potential source. So in part A, V is not constant. Okay, we literally disconnected it. And so because we disconnected it, I have to use this equation to see if I can find the difference between the 2 potential energies, because Q is. And so in part A, I use that energy is Q squared over 2C, and the fact that C is equal to epsilon naught A over D. And so I took this capacitance, I threw it into there, and what I got was that U is equal to Q squared D over 2 epsilon naught A. Now your final energy, if I'm looking for it, the only thing that's different between your final and your initial is that distance. Then I was like, well, Q is constant, that's cool. I know my final distance. I know epsilon naught's a constant, but I don't know what A is. And so I had to get a little creative. U naught, your initial energy, similarly, would be Q squared D naught over 2 epsilon naught A. And what I did is I took these two fractions, I divided them by each other, and so what I said is that UF over U naught is equal to, and I showed the math, and if you do that, you should get something like dF over D naught, I believe, if you do the math correctly. And so they gave us my initial distance, my final distance, my initial energy. I took this initial energy, multiplied it to the other side, so I can say that UF is equal to dF over D naught times U naught. And then for part B, I did the exact same thing, except for part B, I used the CV squared over 2. Because in part B it said that the voltage stayed the same. And so because the voltage stayed the same, that's why I used this one. I kept something that was constant both at the beginning and at the end. And it was kind of the exact same process. Alright, let's see, what else? Would it be possible? See, can you do problem 1 in the fall 2016? I can't send a link. Dang. I wish I had that in front of me. Not quite sure. See, 2001. You can kind of explain it to me. Can you tell me the subject? If you can tell me the subject of the exam, then that will be helpful. I'm trying to think. I mean, we'll figure it out. Like I said, this is kind of practice. Y'all are kind of my guinea pigs, so I apologize for anything that's being kind of tough. We're kind of trying to work out the kinks right now. What I might do in the future, if y'all want, we can print out the 2014, 15, and 16, and we can maybe work through those together. One thing that we could do starting next week, at those times from 2 to 3 p.m., we'll print out all the exams. Let's print out 14, let's print out 15, let's print out 16, and then after I get my lesson, we can run through a couple of exam problems. And then what we can do is whatever problems I didn't finish or I didn't get to see with y'all or do with y'all like during the week, maybe we could do that here. So that's something that we can kind of figure out. Okay. Let's see. Any other questions? If you all have any questions, now's the time to ask. And like I said, I wish we can figure that out. I'm still trying to figure things out too. Okay, so it's basically like problem number 2, but with the switch in between C1 and 2. Alright, let me take a look at this. Okay. So I can kind of explain the concept behind what you would do. I wish I can see the problem in front of me. I'll kind of talk about what to deal with the switch. Okay. Were there any resistors? Was it an RC circuit or was it just capacitors? That makes a difference, because if it's capacitor R's and C's, then we have to deal with extra stuff. But if it's just C's, then just follow the rules to the game that we talked about earlier. And if you have maybe like a capacitor here, and then maybe like another capacitor. I'm not sure exactly what the circuit would look like. Maybe something like this, but I'm not sure. Is it an RC? I don't know. Is it an RC circuit or is it just with capacitors? Just capacitors with the switch between A and B. Find the potential difference between A and B. Okay, so basically, if I'm assuming this right here is A and this right here is B, if that switch is closed for a long time, let's just say that it's, let's put a capacitor right here. I don't think I'll put a battery or something. Okay, so we have a switch right here in between, here at A, in between, like, say, C1 and C2. If it's closed for a very long time, you can treat it exactly like we did the previous one. Now, if it's closed immediately and it says, what's the voltage difference? I mean, it's kind of the same thought process. What I would do, if this is your EMF and this is your C3, C4, what's the potential difference between A and B? Honestly, just do the same thing. I mean, I wish I had more information, but I would say that the V of B is equal to your voltage minus, Q3 over C3, and then V of A, here's our battery, I come around like this, is equal to your voltage minus Q1 over C1, and then whatever these numbers come out to be, the difference between the voltage at A and B is simply just, so your VAB would just be your V of B minus V of A. And like I said, whether you subtract the A and the B or the B and the A, it doesn't make that big of a difference, because what's the distance between 4 and 7? If I wanted to find the difference between 4 and 7, you can do 7 minus 4, which is 3. Or you can do 4 minus 7, yeah, that's a negative 3, but we know that regardless of which way you went, the difference between 4 and 7 is 3. So that's how I would go about doing that one. Right. So hopefully that answered that question. But don't let switches kind of freak you out, okay? Just know that it'll be charging. Maybe the growth and decay, that could play a factor. But those are the equations that we utilized on that last problem. Any other questions? So, if y'all don't have any more questions, like I said, any feedback that y'all have next week, I would greatly appreciate it. I think, since I don't have all 3 exams on me, one thing we will definitely do next time is let's print out all 3 exams. I'll give up my lesson, I'll show you my lessons, and then as practice problems, we'll slowly start chipping away at every exam. And then what we'll do is whatever exam problems we don't finish, we can definitely walk through each one of those types on here. That way it's going to be a little bit more organized maybe. Maybe we can, like if it was this exam per se, we would do a couple of capacitor problems, then we would do a couple of RC circuits, something like that. And so we'll do that similarly for the 3rd exam or second, or the next exam, and we'll figure it out from there. So I really appreciate y'all checking this out. Hopefully this helped. If you have any questions, definitely, I guess save it for next time. You can also text me as well. If you need to, you can either text or email me if you have any last-second questions. Let's see. My contact, most of y'all should already have my contact info, but in case you don't, number is 979-574-2215. And then my email address, if you want to email me personally, just do David Salinas at Spartan-Tutoring.com. So, like I said, this is the first time I've ever done this. I don't even know how to stop the streaming, so I'm going to try to figure this out. Good luck on y'all's exam tomorrow. I will see y'all next week.